Welcome back to our lesson on dot and cross diagrams. This is part 2. Make sure you've watched part 1 first, please. Okay, so let's consider covalent bonding. Covalent bonding, you decided, you looked, it's two non-metals or three non-metals, but it's all non-metals. It's a sharing bond. Now that might look like O2, so you've got two of the same type of atom, but they're bonded together covalently because they're non-metals, or it could be a compound like HCl, hydrogen chloride. You know that as hydrochloric acid, but that's hydrogen and chlorine. Again, they're both non-metals, so it's covalent. So the rules are important here, and if you follow the rules, you can't really go far wrong. So first rule then, it's sharing pairs of electrons, okay? And that means that if one atom shares an electron, the other atom that it's sharing with will also share one electron. However, if an atom shares 2 electrons, the other atom will also share 2 electrons. So you'll never see, for example, 2 dots and a cross. It just doesn't work. And if you have got that, then you've done something wrong. And it's another reason why we use dots and crosses. It just makes it easier to see that. Okay, so the second rule then, they will only share what they need, which means, for example, hydrogen will never share 2 electrons because it only needs 1 more. So it will only ever share 1 electron. Carbon, on the other hand, will share up to 4 electrons because it needs 4. Next rule then, the correct number of electrons per atom. So for example, oxygen has 6 electrons in its outer energy level. If we've done dots to show that, it would have 6 dots, and it doesn't matter what you do with it, it will still have 6 dots. It might have dots in the sharing area, it might not have dots in the sharing area, but it still has 6 dots because there are 6 of its own electrons. However, in total, it has to have 8 because that's a full outer energy level. So if we keep checking these rules, we are going to be on track. So how do you know how many electrons each atom needs in order to become stable? How many they will share? How many will go in that sharing area? Well, look at your periodic table, and it's the same idea as your ions. If you think about group 7, when its ionic bonding, gains 1 electron. It's got 7 electrons in its outer energy level. It gains 1 to become stable. It needs 1, so it will share 1. Group 6, it needs 2, so it will share 2. Group 5, it needs 3, so it will share 3. Group 4 we've not done before, but it has 4 electrons in its outer energy level. In order to fill it up to 8, it needs 4, so it will share 4. Now watch out for hydrogen. This one here, it doesn't, on this periodic table, obviously it's all on its own where it belongs. On your periodic table, it actually appears in group 1 because it has 1 electron in the outer energy level. Now, this is the confusing bit because you're thinking, well, this is not a metal. You're absolutely right. It forms a +1 ion, which is even more confusing, but it needs, if it's going to bond covalently, it needs 1 more electron in order to become stable because it just has that first energy level, so it's full at 2 electrons. So this is your rule breaker. This is the one you've got to watch out for. Hydrogen, it's very small and it only has 1 electron and it only needs 1 electron in order to become stable. So it will only share 1 electron to become stable. So let's consider hydrogen for a moment. So hydrogen, 1, atomic number 1, it has 1 electron. So it needs 1 electron because it's that little rule breaker. So it needs 1 electron, so it will share 1 electron, which means that the other hydrogen will also share 1 electron. So if I follow the rules, it needs 1, it shares 1, okay. This hydrogen here has 1 of its own electrons. However, if I go around the entire shell, 1, 2, it thinks it's got 2, so it's stable. This hydrogen here has 1 electron of its own, but if I go around the entire circle, the entire energy level, it's got 2 in total, so it thinks it's stable. Okay, so let's consider oxygen. So oxygen's group 6, it needs 2 electrons, and therefore we are going to have 2 dots here, sharing 2 electrons, which case the other oxygen will also share 2 electrons. If I consider this oxygen here, it's got 2 of its own, 1, 2. It should have 6 So it needs, so 1, 2, it needs 4 bits more, doesn't it? So let's put those in. So 3, 4, 5, 6. So it should have 1, 2, 3, 4, 5, 6 electrons of its own. But if I go around the entire energy level, 1, 2, 3, 4, 5, 6, 7, 8. So it's stable. This oxygen here, it's got only 2 of its own here, so it needs 6 again. So let's add those in. 3, 4, 5, 6. So it should be 1, 2, 3, 4, 5, 6 of its own. But if I go around the entire energy level, 1, 2, 3, 4, 5, 6, 7, 8. So it's stable. And just doing that double check how many of electrons of its own and how many electrons in the shell is going to make sure you don't draw too many electrons. Okay, why don't you pause the video and have a go at doing a chlorine molecule for me. Okay, so chlorine is group 7. It needs 1 more electron in order to become stable. So it's going to share 1, which means the other one's going to share 1. Okay, if I look at this chlorine atom here, it's got 1 of its own. Okay, it needs 7 of its own, doesn't it? So 1, 2, 3, 4, 5, 6, and 7 of its own. But in total it's got 8, so that's good, that's stable. This one's got 1 of its own. I need to add some more. 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7 of its own, plus that one there, 8 in total, so it's stable. Okay, pause the video and have a go at a nitrogen molecule for me. This is group 5. Okay, so group 5, it needs 3 more in order to become stable, so each is going to share 3. There we go. Let's look at this nitrogen atom here. I've got 1, 2, 3 of its own, 4, 5 of its own because it's group 5. 1, 2, 3, 4, 5 of its own, but 8 in total. And this nitrogen here, it's got 1, 2, 3 of its own, so 4, 5. So 1, 2, 3, 4, 5 of its own, and 8 in total. Okay, so let's take this up a notch. What happens when they mix and match? When you have a compound where you've got different elements and they want to share different amounts? Well, a classic example would be water. And let's just consider water for a second. So water is hydrogen and oxygen. Now you know the formula for water is H2O, but let's just pretend for a second that you don't, okay? So let's think hydrogen here is going to share 1 electron. We know that. And oxygen is going to want to share 2 electrons. Now what you cannot do is go, okay, there's hydrogen sharing 1 and here's oxygen sharing 2, because that breaks the rules. The rules are sharing pairs of electrons and also it'll only share what it needs. So, and it also doesn't make sense, does it? Because this hydrogen here has got 3 electrons in the outer energy level. It doesn't make any sense. So then you have to think, well, okay, how am I going to make this work? I have to remove this X. So I'm going to add another hydrogen, okay? And this is just practice and understanding what normally happens. Okay, and I'm going to move that across there. Okay, and then I've got this other hydrogen also sharing its electron. Now that's already looking better, isn't it? This hydrogen, 1 of its own, 2 in total, it's stable. This hydrogen, 1 of its own, 2 in total, it's stable. But the oxygen, it's only got 2 at the moment of its own, so I need to add some in. It's group 6, so it should have 6 of its own. So there we go, is that 6? 1, 2, 3, 4, 5, 6. And it should have 8 in total. 1, 2, 3, 4, 5, 6, 7, 8. So I know this is stable. And it's just a matter sometimes of playing around. Some of them you'll know. You might get lucky and get one that you're familiar with. But if you don't, you just follow the rules and have a play sometimes until you kind of get something that looks right. But if you follow the rules, you can't really go wrong. Okay, so pause the video and have a go at ammonia, NH3. You'd never need to know that formula by heart. They would give you it if they were asking for it. Okay, so ammonia. So nitrogen, group 5. I can see that here on the periodic table there, group 5. And hydrogen we know is going to share 1 electron, and nitrogen is going to share 3 electrons. It's got 5 of its own, it needs 3 more. Now, from the formula, I'm thinking, well, 1 nitrogen, 3 hydrogen. Because I'm used to doing this, my instinct is to put the nitrogen in the middle, which I'm going to do, and then I'm just going to scatter the hydrogens around there. You'll notice they're not crossing over each other, they're just crossing over the nitrogen. Okay, now I'm going to just go around each of the hydrogens because I know hydrogen will want to share one, and therefore sharing pairs, it would have share one. Actually, that's a sharing pair with nitrogen. Next one, there's its sharing pair, and that one there, that's sharing pair. Are we all done? Well, let's have a look. This hydrogen, one of its own, 2 in total. This hydrogen, one of its own, 2 in total, and this hydrogen, one of its own, 2 in total. So those hydrogens are stable. Okay, let's look at nitrogen. It's got 1, 2, 3 of its own. It should have 5, so I need to add some in. Okay, so it should have 5 of its own. 1, 2, 3, 4, 5, 6. That doesn't seem right. Hang on a minute. It should have 8 in total, shouldn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, I've done too many. Let's just get rid of that one there. Okay, so 5 of its own. 1, 2, 3, 4, 5. And 8 in total. 1, 2, 3, 4, 5, 6, 7, 8. Now, actually, guys, when I was preparing the PowerPoint, I actually did that without thinking that was a genuine mistake, but I've left it in to show you just how easy it is and how the double check stops you from making that mistake. So there you go. Even I manage it. Okay, so pause the video and have a go at methane, please. Okay, so we know hydrogen is going to share 1 electron, and we know that carbon is going to share 4 electrons. It's group 4. From the formula, it suggests that carbon's going to be in the middle there, and I'm going to scatter hydrogen around, making sure they don't cross over each other, they just cross over the carbon. And then I know what each hydrogen's going to look like. It has one, it needs one, so it will share one with each of those. And I'm just going to double check them. That one of its own, 2 in total, 1 of its own, 2 in total, 1 of its own, 2 in total, 1 of its own, 2 its total. So the hydrogens are all stable, and carbon has 4 of its own, 1, 2, 3, 4. So it's actually already got 4 of its own, and 8 in total, 1, 2, 3, 4, 5, 6, 7, 8. So actually that is already done for you, and that is that one done. Okay, guys, if you can do this one, you can do any of them. Carbon dioxide, CO2. Okay, so we know carbon will share 4 electrons, and we know that oxygen will share 2 electrons. And looking at that formula, CO2, I am going to put carbon in the middle, and I'm going to put 2 oxygens either side. Okay. Okay, so carbon can't share 4 with an oxygen because oxygen only wants to share 2. So oxygen is going to share 2 electrons, so carbon will also share 2 electrons. Okay. Let's do the same on this side. Okay. Is this oxygen stable? It's got 2 of its own. No, it needs 6 of its own, doesn't it? It's group 6. So let's add some in. So 1, 2, 3, 4, 5, 6 of its own, and 8 in total. So this is stable. This oxygen, not quite. Let's add some more in. Okay, so 1, 2, 3, 4, 5, 6 of its own, and 1, 2, 3, 4, 5, 6, 7, 8 in total. So that is now stable. Carbon has 4 of its own, 1, 2, 3, 4, and 8 in total, 1, 2, 3, 4, 5, 6, 7, and 8. And that is it. Okay, that is it for this lesson, guys. I hope you found it really useful, and I will see you next time.